So hi everyone, we are back. This is our second video teaching about linear regression. And one fundamental part of linear regression is our cost of error function. This is a function where we try to minimize to find the best parameters, that is the thetas, to our line in order to predict good numbers and set a good line in our example, in our data set. It's like we have x-axis, y-axis. We have all these points that I know there are lines, but
Okay.
and we try to fit a line that best represents all of them. And while we are trying to do it, there is always an error. That is the distance between one point and the line. And this cost function here, we sum all of these errors. That's the difference between our prediction, the h of x, our linear function, and the real value. That's our y. So we will discover now how to better minimize this cost function that we call here j of theta. We can also see it as epsilon, that's the error function. And we will use it first using the batch gradient descent. In Portuguese, it's descida do gradiente. It makes a lot of sense because
Yes.
we are trying to make the error less and low, and we try to fit the line, better line between all the acts that we have in our data. So use the following partial derivative rule as the derivative of fx squared in relation to x is the derivative of the outer product versus the derivative times the derivative of the inner product. That in this case is 1. So this is a notation saying that we are going to update our theta j, and we will multiply it. Since we are minimizing this theta j, we're going to use the minus sign, and we use the alpha, that's our learning rate here, and we will do the partial derivative of j of theta, that's our cost error function, by the theta j. So I just put this function here, and then the first rule that we use is this one, the partial derivative is the derivative of the out product. The 2 goes down.
Basically, in this situation, fx is equals to hx minus y.
Exactly.
Yes.
And the 2 that was exponential here, it comes down, multiplying, and then we multiply this one by the derivative of the inner product.
Just like in the rule that we put.
Exactly. And then remember that our h of x is the sum of all the inputs times the theta, that's ours, is our parameters, and knowing that it's only derivative by theta j, only this one is going to have a value for us. The rest will be equal 0. So
because the derivative of constant is equal to 0.
Yeah. So
and you're derivating only looking at the xj.
Exactly. So all of them are set to 0. Also, it's right here. And we have that the derivative of theta j is equal to 1. And xj is xj. Oh my.
Yeah, no, it's just because you're derivating and theta j, xj in relation to theta j. So this is the constant. Xj is the constant and theta j is the variable. And the derivative of a linear function is just the constant.
Yeah.
That is xj. That's why we have xj here.
And so C, our cost function, it's going to be like that. Really easy to understand. And if you have C calculus in the university, you will remember it for sure. Yes. Let me clear this. Okay. And here we have what we are going to try to do here. We always initiate our linear regression problem with random variables, initial random value, and we try to minimize the error. So at that j, we try to minimize it until find the local minima or global minima, and this linear step is caused also by our alpha here. That's our learning rate. And here we have a simple example and already creating a linear regression model. We use the scikit-learn to make it, and we basically first we say that our x1 is an NP array to remodel the shape of it.
Yes, basically we have to use an NumPy array in order to use properly the scikit-learn. Scikit-learn is a library that helps a lot in making any machine learning thing. So if you will work someday with machine learning, you have to use scikit-learn. In scikit-learn, for some reason, only accepts NumPy arrays. So, and it makes the work easier. NumPy arrays are so easy to manipulate. So, oh no, come on guys, this is a spoiler. So basically, we have to transform both x1 and y1 in NumPy arrays. Y1, we are not doing this right now, but in the future, you have to do that. But for the manipulation that we're going to do here in the model, only x1 has to be transformed in a NumPy array, so that we can use this code. So here we're just creating the model. It's saying that this is a linear regression model. This is a very easy code from scikit-learn.
And then we feed our data in the model, x, y passing as the indefinite variables, and y, I as our definite variables is our labels for this model. And here we see how well our code perform, asking for the score, and our coefficient of determination is pretty good. It's almost 90%.
We already run this for you guys.
Yeah.
You can try by yourself.
And then we find the values of theta 0 and theta 1, where the theta 0 is the intercept of x. We use the model.intercept function to find it. And also we find the theta 1 as the slope of our function, that's the model coefficient. So based on these values, we know that the line equation predicted for those values is y, that is h of x in this case, is equal 0.672 plus 12545x.
Remember that there would be an x here, x0, but it's a dummy feature, so it's always equals to 1. So you don't have to worry about this. So this is basically the y-intercept that you learn at school, and this one is the slope.
Okay, where theta 0.
Oh, and now we already have the linear function that we were looking for. Using the scikit-learn, it's really easy to do that. And it's always the same step by step. Say what the model is, in our case, linear regression, feeding the data set that you created or that you downloaded, and it's done. And you already can see the score. It's this easy.
How well the model perform.
Yes.
And then we can try to predict new values for x. For example, we tried here 20, 25, and 30. And those are the predicted variables. So if you work in a company for 20 years, your salary will be increased.
25 times.
Yeah, almost 26.
Yes.
And it's a good number.
Yeah.
It's a good prediction.
And because you already have the formula here,
Mhm.
so you can predict any y based on any x that you have. And not only for this example, but anything that you can correlate linearly.
Okay, so this is all for today, but in the next video, we will learn more about number equation. That's another way to find these values of theta.
Yes, because if you notice, guys, in this situation, we are jumping and making a lot of interactions in order to find our best parameters. So you have this theta j, and you have to update it a lot of times until you find this. You can see that because, well, the computer does it all, but you do a lot of steps here based on your learning rate that you defined before. And normal equation is basically you doing this in only one single step. Much easier. You guys are going to understand in the next video. So, bye bye. See you in next videos.